The next question I want to ask you guys, a bit off topic, but at what point in time does the object have to actually be data consistent? And let me explain my question using an example. It is obvious that if we have a declaration somewhere of the data object DC, right? Suppose I have DC. Suppose for a second that I had a declaration of a object DC of type DC. So it's obvious that at this point down here, right, after the object has been created, it must be already consistent. It must be of type DC. Whatever type DC is, it makes no difference what type DC is. It has to be already a DC at this point in time. That, I think, there's no discussion. Everybody will agree that's obvious. The question is, when it gets to the constructor, at what point in the constructor do we say that it has to be consistent? And what are my options? So here's my constructor, and we see that we have a DC. I forgot parentheses for the parameters. And we have 5 points that I want to talk about. There's the point number 1 before the constructor begins. There's point number 2 after the prototype list, the header of the function. There's point 3 at the beginning of running the commands. There's point 4 at the end of running the commands. And there's position 5 after the constructor finishes. In which of these 5 locations does the data already have to be consistent? So the point of consistency is actually 5. And what that means to say is the following, which means when we get to point 5, which is once the constructor ends, then the data must be consistent. Now let me explain a bit more. Since we claimed that the purpose of a constructor is to put the data into consistency, so what that is being done is right here, and between 3 and 4. That's being done. It's becoming consistent at this point, which means if you decided that your queue has to have a 1, 2, 3 in the beginning, then when you make sure that happens, that's the number between 3 and 4, that's what that happens. Which means you cannot claim that it can be consistent at 1, 2, or 3 because you never tried to make it consistent. So obviously, if the lines that create the consistency are the implementation of the constructor, which means the lines that we have here between 3 and 4, then up to 4, there's nothing to talk about. Up to that point, obviously, you cannot demand or assume that the object is consistent with its whatever the abstraction is trying to implement is, because the purpose of the constructor is to make it consistent. Now, what's the difference between 4 and 5? Well, there is no real difference except that 4 means that the constructor did not finish yet. Meaning, in a sense, that you are allowed to put in more lines. That's what that means. So, in a sense, it cannot be assumed consistent at point number 4 either, because that point is still a place where you are allowed to add consistency. And therefore, that cannot be a place. Point number 5 is a point where you can assume that you're supposed to make sure, but you can assume that the data is actually really consistent because the constructor has finished working. Just to make an analogy to constant objects, right? Constant objects. So we all know that if you create a constant DC, right? If we go and we created a constant DC, right? Const DC. DC or A or B, whatever you want to call it. So obviously there has to be a place where you can put data into that constant variable, right? Because if you were not able to put in data into that constant variable, so the constant variable is actually useless and meaningless, and nothing, you can't use it for anything. So there has to be a place to put the data into a constant variable. Now think of the constant object, whatever it is, the data of the object data type that is trying to, in a sense, portray is a data that does not change, in a sense, immutable. That's what const stands for. So at what point is the compiler supposed to enforce this immutability of the object? And obviously, since there has to be a place where you're allowed to put in data, so during the constructor, that can't be. So the constructor runs for const variables, object variables, const objects, because that's where you put in your data. So notice that while we're running the constructor, it is actually not data consistent, because the consistency says that it's an object of type DC, but it's also constant. It's also immutable. And during the time the constructor is running, you are changing its data, and there's no problem with that. So you see it's not consistent yet. At point number 5 that we saw before, that's when the compiler locks the actual const of this data, and from this point on, it's actually supposed to be data consistent. And since the constant, the immutability of this data is part of the way this thing is supposed to behave, the compiler locks it right after the constructor. At that point is the point where it's supposed to be consistent with whatever you decided was supposed to be consistent. For that reason, by the way, we have what's called a member initialization list, which means that after the prototype of the function of the constructor, you put this 2 dots, and then you call the constructors of all your partial, should we say, either parents or internal data. Why is that true? Because it could very well be that some of your internal data is constant. And if one of your internal data is constant, one of your data variables is constant, so once its constructor runs, then now the compiler enforces its data consistency. And since its data consistency includes the immutability of that data, how can you in your constructor, once that data is constructed, how can you change its value? You can't. And therefore, we have this member initialization list, which allows me to call a specific constructor as opposed to a default constructor, which allows me to put data into that data member, even though it's const. So we see that once we enter my constructor, all the constructors of all my data members have been executed. And now the compiler is going to enforce their data consistency based on what it knows, obviously. Therefore, you must have a member initialization list. So we see that this concept of data consistency created this idea of constructors, which also created the idea of member initialization list. It's not only an efficiency issue. Oh, call this constructor instead of calling a default constructor and then changing its value. That's also true. You can use the member initialization list to gain efficiency, meaning that we go and we say, okay, let's call the non-default constructor in order to not call a default constructor and then change the value, having a 2-step process. Let's have a 1-step process. But that is a side effect of having this idea of member initialization list. The idea is, in a sense, that all the data members of the object must be consistent before the object itself can be consistent, and therefore their respective constructors run, making them data consistent, and then I can run, making me data consistent. And if one of them happens to be constant, immutable, so you won't be able to change it in your constructor, and therefore you must be able to call some other non-default constructor in your member initialization list. We see from all of this that constructors are part of the actual paradigm. There's a reason why they came along. There's a reason why once the object-oriented paradigm or data abstraction, in a sense, was created, suddenly we have concepts like constructors being created. Because these things their purpose is to make sure that your implementation is data consistent with the actual abstract data type that we are dealing with. Destructors, as opposed to constructors, are less of a concept thing and more of an implementation hack. Meaning to say that since I created my data and I created all kinds of things, I have to clean up after myself. That's a nice trick, but it's less of a concept thing. And suppose we had object-oriented programming, no destructors. Would that be the end of the world? No, you can clean up after yourself in different ways. Then you have an actual destructor cleaning up. The idea is that once I know how I am internally built, so I can clean up after myself better than anybody else. And therefore, we have destructors, but they are not, in a sense, part of the actual concepts that had to come along once we created this idea of an abstract data type. Just to clarify that point even further, think of languages that have garbage collectors. They don't have destructors. Nobody cares. I mean, you could have a disposal or iDisposable or one of those because they say, oh, when I don't need the object anymore, I might want to do something, but destructors are actually not needed because once we discard the data, the garbage collection does the actual cleaning. So it's true that you might do it more efficiently or less efficiently, or you might do it in the right place or the wrong place. But notice how languages that have garbage collections, they do not actually need destructors. They can actually do without them. So that actually just shows and demonstrates the point that destructors are not actually part of the concept behind the object-oriented paradigm, but they're more an implementation thing. Oh, you created something, you clean up. If I have somebody else cleaning up, like a garbage collection, then I don't have to clean up myself. Somebody else can clean up. So this is that just shows that it's not like constructors, which are actually there for more than just an implementation hack, but more of data consistency and other types of concepts of the sort.